Let's look at how the tool calculates net delay. In this module, we'll look at what wire load models are and how they're used to calculate net delays. We'll also identify the different file formats that are used in the different tools so that you can calculate the wire delays. You use different metal layers to connect different cells in your design, and these metal layers become the interconnects or the wires. And they inherently have a delay because of the resistance and capacitance of the interconnect itself or the metal layer itself. So this interconnect delay is also known as wire delay or net delay. And what you would notice is that all of these interconnects are naturally positively unate, and also the net delays when calculated are actually typically calculated from 50% of the input to the 50% of the output. And the timing arc of the net basically connects the pin to pin timing arcs of the cells. And when you want to combine all of these different timing arcs into one single path, you actually traverse through the nets, through the cells, and so on, depending on the transition that is happening, whether it's rising to falling, falling to rising, rising to rising, or falling to falling. And all of these different combinations combine, and most tools they use these different rising and falling calculations and look for the worst case delay, and that worst case delay for the entire path is what's used later on for verification against the timing constraints. Physical tools actually use routing and extraction to determine the actual wire delays, but the front-end tools like synthesis tools do not have that luxury, so they need to rely on wire delay estimation. So wire delay estimation can be done either through wire load models or some kind of layout estimation tools like the one here, it's physical layout estimation, PLE. So either one of these can actually be used. And one of the things to note about wire load models is that wire loads are statistical and they're calculated based on the nearest area. So based on a block size, we determine what the wire length must be and use the fan out end loads to accurately estimate the maximum wire length that would actually be then used to calculate the resistance and capacitance and thus the delay. So this whole thing could actually be very tedious. So even identifying the correct block size for wired loads is actually difficult. So, and then for correlation to the actual place and route tools, again, it becomes really difficult even with the custom wire load models. So, but one simple thing is that the wire load models are there and you can actually use them. So Foundry supplies these wire load models and you can actually plug them in along with your libraries to calculate your delays. Whereas nowadays with the PLE tools, if you provide a left library, which is the layout library, and the capacitance table and the floor plan, they try to calculate again dynamically, but still it's a measured delay. But these kind of correlation wise actually seem to be better than the wire load models. So some of the types of routing that you see here are actually what is employed by the physical tools. And now these wire load models and PLE should actually correlate to those kind of routing models. The wire load models are calculated based on the average statistical net length over many designs. And therefore, because you use this kind of Poisson distribution and determine what is the average net length for those nets in a certain block size, you actually come up with these average statistical values that you then plug in to determine what is the corresponding RNC, and the resistance and capacitance, and then you based on that length, and then you calculate the delay of that particular net based on that. So obviously these are statistically weighted, and you have these wire loads that are sort of pessimistic because of that inherent statistical behavior, and they might be unreliable for some designs. But because they provide a good estimate, you still could use them for critical path analysis, and people have been using them, especially right after synthesis stage and so on and so forth, and also as a good starting point for synthesis. So basically, you determine an area that a particular net fits in, and from there, you use the wire load selection table and select the block area that encloses the area of the net, and then you use the wire load model to estimate that particular wire length, and then you use the capacitance multiplier and resistance multiplier to determine the actual RC, or the delay of the net. And so therefore you basically start out with these block sizes. And so depending on the mode that is used, so there are multiple modes, that is the top mode, the enclosed mode, and the segmented mode. So depending on the modes that are being used, varying block sizes are selected for the wire load model selection table. And so you can also generate these custom wire load models based on your design from specific place and route tools, and you can use those instead of using the statistical wire load models that are provided by your library vendor. So basically this example shows the wire load selection table, and if the block area is between 0 and 203, then basically the tool selects the B.5.5 wire load model. So the actual wire load model kind of looks like this, where you have these kind of resistance multiplier and capacitance multipliers, and the RC is now calculated based on the capacitance of the wire times resistance of the wire. Try this activity to test your understanding. So initially when you start out with your synthesis, you're using the wire load models, but then when you get to your place and route, and your place and route is done, then you now can generate the extracted data, which is either in the form of a SPEF or an SDF. And so this extracted data can be passed back to your synthesis tools, and this passing back is called back annotation. So you can actually send that information back to synthesis to get more accurate timing data for your net delays. And synthesis can now do a better job at optimizing the rest of the design based on the available information. Extraction tools can actually create models for your RC network, and then use that RC network to come up with some sort of compression mechanism, and so therefore the reduction mechanism, and generate these models, either 2D models or 3D models or 2.5D models of your layout. And basically those RC models, when reduced, give you either the RSPF or DSPF or SPEF. The SPEF is the widely used format, and this is what is later on by the delay calculators converted into actual delays. And you can actually take either the SDF to feed back into your synthesis, or the SPEF itself can actually be used to feedback. So either way, this process is called extraction. So one of the steps of back annotation would be delay calculation. If we are feeding the tools delays of the nets, then obviously we need to have a delay calculator that actually does that portion of converting your RC network into a delay network. And so that process is called delay calculation, and usually statistical analysis requires the net delays be provided either through an SDF or the SPEF then converted internally through the delay calculators and then used to plug in the net delays when doing your optimization. So either which way, those net delays are calculated, and so delay calculation plays an important piece of your whole back annotation process, and the accuracy of your net delays depend on both the extraction tools as well as the delay calculation mechanism that is being used. Different formats provide different levels of accuracy and run times. So some of the larger file sizes come with longer run times, and therefore, it may take more time to actually generate these particular uh, files. And of course, when you actually reduce them and make it simpler, it's actually easier for human interaction, it's easier to debug, and also the delay calculation is actually something that is happening in either the front end or the back end, depending on where you basically do your delay calculation. So you can start out with DSPF, or you can start out with the SPEF and then bring that information directly into your synthesis tool and then let the synthesis tool do the delay calculation, or you can actually do the delay calculation ahead of time and then bring in an SDF. So either which way, it all depends on what formats are being used, what are the delay calculators. So you actually kind of, uh, try and justify the runtime with the amount of accuracy that you prefer. And so you generate these kind of correlation numbers that correlate between your front end tools and your back end tools and sacrifice some accuracy so that you can actually meet your design goals faster.